Let's look at triple integrals in cylindrical coordinates. We have used triple integrals to find the mass or center of mass of a solid. The mass m of a solid t is m equals the triple integral over t of delta of xyz dz dy dx, where delta is the density of the solid at the point xyz. We saw that when we worked with double integrals that sometimes we need to convert a double integral from rectangular to polar coordinates in order to evaluate it. Similarly, we sometimes need to convert a triple integral from rectangular to cylindrical or spherical coordinates in order to evaluate it. For example, evaluate this triple integral from -3 to 3, negative square root 9 minus x squared to square root 9 minus x squared, 0 to 9 minus x squared minus y squared, x squared dz dy dx by switching to cylindrical coordinates. When we switched a double integral from rectangular coordinates to polar coordinates, dy dx became r dr d theta. Similarly, when we switch a triple integral from rectangular coordinates to cylindrical coordinates, dz dy dx becomes r dz dr d theta. So they're very analogous. So the triple integral of f dz dy dx becomes f r dz dr d theta. Let's change the integrand f. We use the same equations as before to convert the integrand f from rectangular to cylindrical coordinates. X equals r cosine theta, y equals r sine theta, and x squared plus y squared equals r squared. So in this case, f of xyz is x squared, which is r cosine theta squared, comes from this. In other words, it's r squared cosine squared theta. So x squared dz dy dx, the x squared becomes r squared cosine squared theta, and dz dy dx becomes r dz dr theta. Multiply it all together and we get r cubed cosine squared theta dz dr d theta. Now let's find the new limits of integration by looking at the solid we're integrating over. Z goes from 0 to 9 minus x squared minus y squared. In cylindrical coordinates, z goes from 0 to 9 minus r squared, and that's because r squared is x squared plus y squared. And that's basically what we have here, 9 minus the quantity x squared plus y squared. What region in the xy plane are we integrating over? Because we know the limits of integration on z, now let's find the new limits of integration for r and theta, and those come from x and y. Okay, y goes from negative square root 9 minus x squared to square root 9 minus x squared, and x goes from -3 to 3. Y equals the square root of 9 minus x squared. What is that? Well, let's square both sides and get y squared equals 9 minus x squared. In other words, x squared plus y squared equals 9. This is a circle of radius 3 centered at the origin. We are integrating over the entire circle. So r goes from 0 to 3, and theta goes from 0 to 2 pi. Again, the reason we know we're integrating over the entire circle is that the bottom half is negative square root 9 minus x squared, and the top half is square root 9 minus x squared, and x is going from 0 to 3. So we get the entire circle. Okay, so z, as we've seen before, goes from 0 to 9 minus r squared. We're integrating over the entire circle of radius 3, so r goes from 0 to 3, and theta goes from 0 to 2 pi. And this is our integrand. Okay, integrate with respect to z, and we get zr cubed cosine squared theta, as z goes from 0 to 9 minus r squared. Plug in 9 minus r squared for z, and this is what we get. Plug in 0 for z, and we get that. So let's multiply this out. Let's multiply this out more specifically. So we get 9r cubed minus r to the fifth, cosine squared theta dr d theta. This is as r goes from 0 to 3, and theta goes from 0 to 2 pi. Integrate with respect to r, and this becomes 9r to the fourth minus r to the sixth over 6, cosine squared theta, as r goes from 0 to 3. Plug in r equals 3, and we get this. Plug in r equals 0, and we get nothing. So let's simplify this. When you multiply it out, you end up with 243 over 4. It just works out that way, cosine squared theta. Let's pull the 243 over 4 to the outside, and let's rewrite cosine squared theta using that formula we saw in college algebra and trigonometry or in pre-calculus. Cosine squared theta is 1 minus cosine 2 theta all over 2. Again, that's not an antiderivative. It has nothing to do with calculus. That's just a formula for cosine squared theta. Okay, now let's integrate this with respect to theta. Integrate it from 0 to 2 pi, and this is what we end up with. The antiderivative of half is half theta, in other words, theta over 2. The antiderivative of cosine 2 theta over 2 is sine 2 theta over 4. So when we plug in 2 pi and subtract what we get when we plug in 0. Again, same thing over here. Plug in 2 pi, plug in 0. This is what we get when we plug in 2 pi. So plug in 2 pi for theta, we get that. Plug in 2 pi for theta, we get 2 times 2 pi, which is 4 pi. Yeah, but sine of 4 pi over 4, that's just going to be 0. And of course, when we plug in 0, all of this stuff over here is just 0. So we end up with 243 times 2 pi over 2, which is just pi, or in other words, 243 pi over 4. Now, how do we know when we should switch a triple integral to cylindrical coordinates? We should do this if the region in the xy plane we are integrating over is a circle or part of a circle. That's what we saw this time. We saw the entire circle. Or the integrand has x squared plus y squared under a square root sign, like the square root of x squared plus y squared, or the square root of 9 minus x squared minus y squared. That's a dead giveaway. But if the solid we are integrating over is a sphere or part of a sphere, then we should switch to spherical coordinates, which we'll see next.